let me talk about some new way of writing the derivative. So far when we had f of x equals to, say, sine of x, then we used to say f prime of x is equal to cosine of x, right? Now, there's another way of writing down the derivative, and this symbolism is called the Liebniz notation. Okay, so these two are the same thing. Okay? So when you write df dx, that means you're differentiating f by x. Okay? The Liebniz notation has an advantage when your variables, they're more than one variable. For example, suppose you wanted to know what's let's say you have f of x equals to t times x plus b or something. Okay? And if you just write tx plus b prime, then I mean usually you take this prime to mean derivative with respect to x. X is the variable, treating t and b as some constants, right? But in some rare contexts, t is the variable and x could be a constant. So this symbol, if you just say prime, it's kind of ambiguous. Are you trying to differentiate with respect to t, considering x and b as constants? Or are you trying to differentiate with respect to x, considering t and b as constants? But if you write it like d dx of tx plus b, then it's clear that you're really thinking of this as a function of x, and t and b is some constant. Okay? Now, for those of you who are curious to know what this derivative is, let me explain. Say if you consider t and b as constants, then you just have to differentiate x. So x has to be differentiated, and then because this constant is by itself, it's not attached to anything, this has to be differentiated. And then you have derivative of x being 1, and derivative of constant is 0, so the answer would be t. Okay? Yeah, but that's a secondary matter. I really wanted to say that this thing called Liebniz notation is handy when you're trying to differentiate with variables other than x, or sometimes if you have other letters that look like variables. Okay. By the way, this notation is called Newtonian notation. And this one is called Liebniz notation. Okay, along with the Liebniz notation, I want to add one more thing, another symbol. That's if you have, say, some function, and you differentiate this by d dx, sometimes you want to evaluate that derivative at some point because you want to know the slope of the tangent line at some point x, or it could be you want to know the rate of change of the function at x. So you have to evaluate this after differentiating, right? In that case, you use this symbol of bar with x equals to some number. So suppose we have 2 or something, right? What does that mean? That means you first differentiate and then this number has to be plugged in. Okay? So that's 2x. If you differentiate x squared, that's 2x. And then you're plugging in x equal to 2. That gives you 2 times 2 equal to 4. That's what this symbol means. Okay? Now, why would it be wrong to just put 2 now and then just differentiate? Yes?
It'd be completely different. Well, if it was a different...
For example, what is d dx of 2 squared? No. 0. Why 0? Because 2 squared is a constant, right? So even if it looks like a function and you wanted to apply this, you can't because this is a constant number. Does this have x in there? It doesn't have any x in there. So does this value change as you change x? No, it doesn't. Okay? Now think about what this means. This is trying to measure how much this value will change as you change x. That's what it means, right? If you change the value of x, this doesn't change. So what is the change of this 2 squared as x changes? Nothing. It doesn't change at all. That's why you put 0 there. Okay? Yeah. I mean, another even more confusing question that's also my favorite for the exam is putting something like pi squared plus e to the third. Something like this. I mean, this one looks very much like x differentiating x squared, and e to the third looks very much like this one, but none of these rules apply here because your pi is a number, it's 3.14 something, right? And you're squaring it, so it's another number. E is a number, 2.71, and this is cubed, you're just multiplying 2.71 3 times. So these are still constants. Does it have x in there? No, it doesn't. If it doesn't have this variable x in there, does it vary if you vary x? No, it doesn't. Therefore, what's the answer for this derivative? 0. Okay. All right, so knowing these symbols, let me put the first question, exercise question for today, example question for today. All right, let me erase this too. Example 1, let f of x equal to x times sine x over x squared plus 1. Compute df dx evaluated at x equals 10. So let's try to solve this. Okay, the first thing that you notice when you try to solve this is because you're trying to differentiate, you have to differentiate, but it's a fraction, right? When you're trying to differentiate a fraction, what must you use?
Quotient rule.
Quotient rule. It's a must. It's not an option, okay? You have to use it. So here's the quotient rule. The quotient rule says you differentiate the high one. This is the high and that's the low. So high d, low, minus low d high over low squared. Okay. Now, yes?
Isn't the derivative of the top one cosine? This isn't the derivative of sine.
Oh, I didn't differentiate this yet.
Oh, okay.
I still have a prime, okay? So at some point we'll be getting cosine at some point, okay? Don't worry. Yes?
I just wanted to make sure cosine, the derivative of cosine of x is negative sine.
Oh, yes, thank you. There's a negative here.
Okay, thank you.
Thank you. All right. Yeah, I forgot that. Okay, now let's try to differentiate this. Let's try to differentiate x sine x. What's the derivative of x sine x?
Do I have to use the product rule?
You have to use the product rule because it's a product of two things. So you have to differentiate the first one times the second one, x squared plus 1, minus, then if you differentiate x squared plus 1, that's just, no, sorry about that. I forgot. Back to, sorry, x times sine x, so you differentiate x times sine x plus,
Differentiate sine x.
differentiate the second one, this is the derivative of this one. This is the product rule applied. And again, product rule is something that you must use. It's not an optional thing. You have to use it. If you just simply say, oh, x prime is 1 and sine prime is cosine, and you write 1 times cosine, you don't get anything right. It's just completely wrong. You have to use the product rule. X squared plus 1 minus 2x, because x squared differentiates to 2x, and 1 is a constant. When you differentiate 1, it's gone. X squared plus 1 squared. Okay. All right. Now let's continue on. This is 1, so that's just sine x. X cosine x. X squared plus 1 minus 2x squared, because x times x is x squared, sine x over x squared plus 1 squared. Okay. All right, now let's evaluate this at x equal to 0. Okay, so just put an x equal to 0 here. See, this means only after you've completed the derivatives you may plug in 0. Okay? I couldn't plug in 0 here because I still had some more derivatives to compute. Okay? Only after figuring out all the derivatives, I may plug in x equal to 0. And if I plug in x equal to 0, oh, I just got 0. All this work just gave you 0. Okay. I should have put a cosine there. That must have been better. Okay, so this will be 0, that's 0 because it has x in there, that's 1. That will be 0, this will be 1, so you have 0 on the top. Both of them give 0, these two both give you 0, and down here will be 1, so it will just be 0. Okay. So that's the first example. Now, I'll give you some time to try something similar. Example 2, try y equals to, say, 3x cosine x over x plus 2. Okay. So for this one, try dy dx at x equal to 0. Try this question on your own.